If you are just joining us, let me tell you what's going on. This is not the beginning of the class. We already reviewed about 5-10 minutes. Laws of motion and type of forces encountered in mechanics. Weight, normal force, tension, explain the nature, connect to the previous lecture. Discussed already about the nature of the normal force. In this case we use the model. Again, I'm just filling you up. We already did this with the students. Atoms. The question was, why don't you go through your chairs? Why don't I go through the floor, pass through the walls, although I'm still working on why the whole Earth takes this block and pull it, the whole Earth, but the table will be enough to stop it. Why is that block not passing through? Atoms, we agree. We used remote control answering keyboards. I got answers for my questions. What's the type of this force? What's the type of that force? Obviously, we finally agreed it's a mutual action, reaction, electromagnetic repulsion, atoms coming too close to each other, summation of all the forces acting on the block up, normal force, summation of the forces acting down, and we had some discussion about that. Still normal force. However, if the block is at rest, then we can equate that normal force with the weight. This will be helpful. It's not the topic of today's class, but it will be very helpful to understand the topic of our class, which is unknown, mystery. I didn't tell my students. I said from the beginning, we'll figure it out. So bear with me. Again, weight, normal force, tension, are they enough? For centuries, people believed that you do need a force in order to maintain a motion. As soon as that force disappears, objects will stop. But I already figured it out, and we are set with my students. We understand what was the mistake in that statement. We understand what means the law of inertia. We understand what means Voyager 1, Voyager 2, moving in space with no propulsion, far away from many other objects, going at the same pace. So it appears that, and now I will connect with my students. Yes, Anna? What's going on? Yes, it's easy. And that's the mystery. That's the topic today. You mentioned the word, the magic word. It's probably friction, what's going on here. What is making this block to actually stop? If I make friction to almost disappear, this is a hovercraft, pushes air down, what do you know? For a small push, I almost have a uniform motion, creating a cushion, friction force almost zero, therefore, according with the principle of inertia, that object is maintaining a state of motion, in this case uniform motion, as long as there are no forces from outside. But this definitely feels a force. A block on an incline, definitely, if this will be perfect ice, it should slide down. Yes, Bob, I know. But we're saying, increase the angle, Professor, so if you want the block to go down. So, yes. Oh, that's a very good observation. I have Ginger here telling me that we might be talking not just about friction, but maybe about two types of friction forces. One in which the object is still at rest, and one in which the object is in motion with acceleration or not. So if we apply a force, so we don't have just a block standing Fm equal with Fg. If we apply a force, I have a scale here which can show me the force. You see, the scale is showing a force, however the block doesn't move. Why? What is the answer? Very good, thank you. It's friction. What kind of friction? Rest. Let's call it static friction. But I can do this, right? And we will call it, yes, the good word, dynamic or kinetic. So definitely I can see this. Red arrow, visible, my pull. You can see it here, different values. I increase my push, still doesn't move. Why? Because there's a friction force, which we call it static. What's the relationship between them if this doesn't move? Mary? Thank you very much. They should be balanced. They should be equal to each other. So probably if I change my push, thank you, the friction force static will change accordingly such that they are all the time equal with each other. Something like, I'm trying to show you also the animation like this. It appears, yes, this kind of friction prevents objects to be moving. It's against the motion. What if I insist? Take a look. Make sure the table is clean, otherwise those particles of dust can act like the logs on which the Egyptians rolled the big stones of the pyramids. So make sure that the table is clean. We'll do this lab soon. Okay, I'm pulling. What happened? Did you see? Oh, you didn't see. But, oh, you're here. What happened? The needle, which indicates the force which is required to maintain the motion, appear to actually go down. Let me do it again. While I maintain a uniform motion. Please summarize for me. Thank you. Friction force kinetic appears to be less than the friction force static. Any friction force static? Thank you, Mark. The maximum, since the friction force was changing all the time. As soon as I go into motion, the friction force will change into a kinetic. And I can try to show it on a much bigger scale. The same experiment. Pull. I'm increasing my pull. Probably the friction force is matching balance force until threshold. Motion. Needle decreased because I'm moving. Kinetic friction probably less than maximum static. And we can see this also nicely with our incline. Okay, I can slowly increase the angle. What's that? It appears, yes, as soon as it moved, it appears to move with acceleration. It kind of makes sense. Makes sense because, again, the friction force kinetic is decreasing lower than the maximum static. So maybe if I really want to match the static, we should do it slower and keep on tapping so it's barely moving. You see, it's barely moving. I have almost a uniform motion, so it's quite at the beginning is when we leave the regime of static going to the kinetic. If I bump into, I can manage to have a uniform motion, which is from the dynamics point of view the same as V equals 0, rest. Okay? Examples? That's the beauty of physics. Connect with your everyday life. And this is easy. You guessed my mystery quick. You said the magic word. We talk about friction. That's the topic of our class, our lesson today. So in here, students will offer me examples. I'm just showing you how I will behave in class, so I will go quick. Probably add to the examples. They might ask, most of my students are asking, what's the ABS system? Professor, you said the motion impedes, the friction impedes the motion. But I might have, yes, Anna. Professor, you are actually being able to move. I know, because I have a grip on the floor. Yes, it will be very hard to walk on ice, we know. Or to move from dry pavement with driving your car on ice. The wheels will just spin with no outcome. So, let's make the difference. In this case, because my foot is static, not moving in respect with the ground as I walk, I'm relying that I'm not going to slide. That's why I am able to walk. If it's slick, I might fall. The same with cars. So, I will try to encourage my student to connect to the everyday life experience and maybe match some of the examples, maybe add some more. A climber, pushing. You create the grip yes, that's a normal force. That push is a normal force. So guess what? That's actually a very good observation. That's why we insisted talking about the nature of the normal force, because we connect to the friction force. Probably they are interrelated. Static friction. We don't want to slide. Well, ice. You probably will slide if you don't have the right equipment, in this case, crampons. Again, another example. Sweaty hands, exercising. Well, put your hand in a glove and you will get the grip. Sliding, clits, pull. This is a fun example I usually do in class. I will pretend I'm doing it here. I'm able to hold this bar because I have a good grip. My hands are pressing, normal force, on the bar. I will take some oil. Usually students like that. And guess what? It's gonna slide out of my hand because I cannot have a good grip. What changed? Yes, it's probably the relationship between the two surfaces, which, yes, we should analyze. We should analyze. We talk about what means ABS, what means stopping distance in the case in which the wheels are freezing and you start to slide, kinetic, no good, lower, or the computer keep on pumping the brakes even quicker than human can. That's why you have that system such that they allow the wheels to turn, such that you are in the static regime, so you are not skidding. But this is the point we want to make, because we want to actually connect. We kind of see it's a nebula yet. Friction force is connected with apparently how much this block presses on the surface underneath, which my students know it's not always the weight, yes, part of the weight, we know, a component, tangential, or leaning against the wall. Normal force means perpendicular, we already discussed about that. We want to actually go in more detail and could try to connect friction force with normal and with what means the two surfaces. So I will ask my students, so I'm back in class, smooth, nice, flat. Is it real? Probably I will get answers, yes. It's a very simplified version of the reality. If we take a look the same way we took a look with the normal force, we're gonna see a landscape. Invisible for our eyes, but probably imperfections which are interlocking to each other. Surfaces just look smooth because we don't have the power of resolving those details, which are much smaller that we can perceive. But friction is connected with this interlocking of mountains and valleys. And although it might be a simplified version of what is the complex reality, to unlock, unstuck an object which is at rest, apparently it takes more force, as if you will have to take the blue all the way from the valley to the top of the mountain. Obviously blue stands for the block surface, red stands for the table surface. So it's much easier now to just hit from one mountain to the next than to go all the way up to the mountain, from the valley to the top of the mountain. And we'll try to give the same explanation for the nature. This is calculus based, it's not much calculus involved here. It's still conceptual understanding, this is still introductory physics. Yes, you were right, those are atoms belonging to the two surfaces. So if I conveniently choose atoms, right now, let's say the block is not moving, is at rest. If I choose a block which is not pushed, then I do have those forces we already know will sum it all and give me the normal force, which is what the block feels, that's why it doesn't fall through the surface underneath, and the equivalent, the reaction to that. What if I push the block? Well, then atoms which are neatly pushing on along the surface necessarily or perpendicular to the surface will start interacting, coming too close to each other, repelling on some arbitrary direction, angle. Yes? Very good observation. Mandy said, Professor, what if we project them? Because we've learned this, when we have forces on an angle, it might help us. Yes, I can. Yes, we can. We will project, and guess what? We can connect back to the macroscopic explanation. The component which is perpendicular to the surface will basically be the normal force. The component which is along the surface, so in this case, when I'm pushing, is inhibiting the motion, against the motion. The component will be action in reaction. I can probably, if I have enough grip, I can pull the whole table just by pushing on the block without touching the table, because of the interlock, because of the two friction forces which are acting along the surface. They are perpendicular to each other, but they are related to each other. Floating hovercraft, no friction force. If I would lift this so the surface underneath doesn't feel those atoms, they are not interlocking, then I'm free of that friction force. Otherwise, I will connect to the normal force. So what's going on farther on, the connection between friction force and normal force appears to be directly proportional, including the quality, the roughness of the two surfaces. Thank you.